Dr. Bromwich is a professor in the Department of Geography at The Ohio State University and also a senior research scientist at the Byrd Polar Research Center. His research focuses on global climate change and high altitudes resulting from local and tropical influences, as it is studied using climate models and atmospheric reanalyses. Furthermore, he is part of a system reanalysis project that concentrates on the behavior of the coupled atmosphere, land, ocean, sea, ice system of the greater Arctic, which has been reconstructed since 2000. Finally, he is involved in the polar version of the regional WRF model that is being developed, tested, and applied to climate variability and change problems in both polar regions. A few recent publications. There's a submitted paper contrasting the regional Arctic system reanalysis with the global ERA interim reanalysis. New view of Arctic cyclone activity from Arctic system reanalysis, and Arctic summer atmosphere and evaluation of reanalyses using ASCOS data. Thank you very much for volunteering to present today.
Okay.
And I have to say, David was particularly excited by this topic. I think since a lot of the news media captured the excitement of the paper, of the work last year of NASA, we really wanted to allow this information to be presented to the public. Sometimes the news media misportrays it, but this is a time for us to get a sense of the depth of what that paper meant and should mean for the future. Thanks.
Okay, so thank you, David Elliott, for giving us a heads up on John Mercer. So basically what I'm going to do is I'm going to present to you where the debate that John articulated based on not very much information, but a lot of very basic intuition, and what's going to happen to West Antarctica. So that's what I'll try to talk about today. Julien, who is a co-author here, did a lot of work of putting this together, and I am with, it was the Institute of Polar Studies when I first came to Ohio State University, then it became the Byrd Polar Research Center, and now it's the Byrd Polar and Climate Research Center. We have to have climate in our name, so this is the third evolution of the name. Okay, so here's an outline of what I'm going to talk about. Setting the stage, actually we can probably go through that quite quickly. Try to articulate why John called it a threat. Talk about the signs of a changing climate, and we can debate whether that's climate change or climate variability. What we can't debate is the ongoing evidence, particularly from NASA, from a lot of satellite observations of changes of the West Antarctic ice sheet, and where might this go in the future. Okay, so setting the stage. So we've already seen this. So West Antarctica, it's in the, just to review once again, we've got West Antarctica, which sits in the Western Hemisphere, okay? And the East Antarctic ice sheet, that's the big ice mass I'll show you in a moment. I'll also mention the Antarctic Peninsula, which has come up already, and South America sits up here, and the Patagonian ice field sits in the southern part of South America. And I know from John told me that there was literally meters of precipitation in the Patagonian area. So he was a real pioneer of investigation in that area. So how much water sits in the West Antarctic ice sheet removed from the ocean? Depends on who you listen to and how you divide it up. It's something like 3.5 to 5 meters of global sea levels. Not this often, entirely into the ocean, and global sea level on average comes up about, so you multiply that by 3.2 or something like that to get into feet. So this is a substantial rise in sea level if it was to happen. Okay, so we need to talk about some terms. We've always got to talk about terms, right? So what is called the grounded ice sheet means that is not floating on the ocean, it's on land, okay? The other part here is things called ice shelves, which are floating on the ocean, okay? But as we've already heard, their function is to hold back the ice sheet. So the ice sheet moves under gravity, it comes out of the sky as snow, it's compressed into ice, and then moves under gravity. And then it discharges into these ice shelves, and these ice shelves restrain, and they actually hold back the flow of the ice. So what happens to these things has a lot of impact on what happens here. Okay? So Antarctica releases ice into the ocean. I think I've said all of this. Ice shelf melting does not directly contribute to sea level rise, but it can contribute indirectly by regulating what's happening upstream of the ice shelves. Okay. The ice is in motion because it's driven by gravity, and the elevation above sea level varies, and it doesn't do things uniformly, but it moves and converges into these places called ice streams, which are fast moving. And here's the scale, if you can see it down here. It's about 1 kilometre a year. So for ice, that's relatively fast moving. And I'll come back to talk about these two places. Okay, so this is West Antarctica here. This is the East Antarctic ice sheet. And there's two important glaciers, Pine Island and Thwaites glaciers, which we'll talk a lot about. And in 1981, another alumnus of the Ohio State University Institute of Polar Studies, infamous individual called Terry Hughes, called Pine Island and Thwaites glaciers the weak underbelly of the West Antarctic ice sheet. And he was talking about these areas here. Okay, so we'll talk quite a lot about those two places. Okay, so why did John want to call this a threat? Okay, well, here's this famous paper. And it really was a prophecy, and as we all know, prophets are not necessarily welcomed in their own countries. It's a famous quote. And he was with the Institute of Polar Studies, so this started off International Geophysical Year. And basically, the story is pretty much, in very broad terms, the same as he wrote about as we're talking about today. It was 1978, and I know this was a very controversial paper when it came out, and I know John used to be invited to meetings to give his, quote, threat talk. So I won't be giving a threat talk, at least I don't think. Okay, so because we have these ice sheets, when you sit on the top of an ice sheet and you go down, you actually go back far into time. And so we can extract these records from ice cores of what climate was like in the past. And these are ice cores from, this was Epica, which was in one part of East Antarctica. Here's Vostok, there's another deep ice core. Okay, time going back in the past. So here's 450,000 years ago. Actually, we can go back about another 350,000 years. And this is a proxy of what the temperature does. Okay? And here's today. And you see the cycle is roughly 100,000 years from these big ice cores. Okay. Now there was the last interglacial, which we're in right now. Okay. It was called the Eemian interglacial, which is right here. Okay. So it's cold down here, warm here, and we are in an interglacial, which is relatively warm. It's about 10,000 years old. If you were doing what has happened in the past, you would say, okay, sometime in the near future, we're going to go down into the next glacial period. Now, an important thing about the Eemian is that it may be an analog for our future climate state. And probably the most important thing was that global sea level was substantially higher during this time period, which is actually warmer than today, by something like 10 meters, something like that. So maybe as much as 30 feet higher than today. Okay? There's not a lot of direct evidence. We know how high it is. There are only a limited number of places that you can get that much water into the ocean. And West Antarctica is definitely one. Okay? And there's some other lines of evidence that suggest that at a time when it was warm or warmer than today, a good fraction of West Antarctica was in the ocean, it was melted off. Okay, we talked about a marine ice sheet. Okay, this is when you take all the ice away from Antarctica. You don't allow the crust to respond because it had all the weight of the ice sitting on it. And in the yellows and the reds, it means the bottom is above sea level. Okay, so here, this is West Antarctica. You can see there's a lot of blues. Okay, which means the bed that's sitting below the ice sheet is below and well below sea level. Okay? And if you take a cut through that, okay, so here's, you can see how much bigger the East Antarctic ice sheet is, right? There's a lot more water. There's 10 times more sea level sitting in that ice sheet as there is in West Antarctica. Okay? But the important thing is, first of all, here's sea level, okay, that a lot of the bottom is below or well below sea level. So that's one ingredient of a marine ice sheet. The second is that the bottom has to slope into the interior of the ice sheet. Okay? So marine ice sheet has to sit on a bed which is well below sea level that slopes into the interior. As you can see, there's some very, very deep parts. This is named after Charlie Bentley, I think. I think that's Bentley subglacial drop. And then the other thing is it sits on marine sediments, so things that came from the ocean originally. Okay? And it turns out that this part of Antarctica has also got a lot of geothermal activity. So there's heat coming up from the bottom going on. Okay? And in fact, if you know about this deep core that they recently drilled in close to Byrd Station, I'll get to Byrd Station in a minute, they expected it to be over 100,000 years old. I remember sitting in the discussions. It's only about 70,000 years old. And the reason is because it's being melted off at the bottom, probably. Okay, so this is just another aspect of the story that this is not a great place to have an ice sheet. Okay. Signs of changing climate. So today we've got a relative wealth of observation today, right? 2014. We have these satellite transmitting automated stations. Okay, so there's about 100 of those sitting over Antarctica. They transmit the weather observations to space, temperature, pressure, relative humidity. There is this, so it's relatively well instrumented today. There's also these ground-based GPS units, which are put out on rocks, and basically what they track, if you know GPS, you can track the vertical elevation very, very accurately, and so you can actually see that the ground of the rocks is slowly coming up, because in the last glacial period there was a lot more ice sitting over this area. So the ground-based GPS, which is the same constellation of spacecraft which is there to deliver the nuclear missiles with pinpoint accuracy put up by the US military, and I've got this vast collection of domestic applications, including in your vehicle at mine. We've got more satellites today than we know what to do with. We tap a small fraction of the vast amount of information coming down. And NASA flies some fancy aircraft, you know, like has airborne lasers, airborne altimeters, airborne radars to look through where the surface of the ice is and to the bedrock. But you don't have to go back very far, and detecting climate change in West Antarctica, as is the case in the dry valleys, it's a bit of a challenge. So to determine that climate is actually changing, we need to have a baseline or a something to what it looked like before climate began to change. So the problem here in West Antarctica is most of the observations now, which are about weather observations, have only been around for 10 to 20 years. So that's not very long. And it turns out that this is a very variable place on planet Earth. And so they have large variations in time and space, and climate change is difficult to establish with certainty. All right, for processes with little month-to-month or year-to-year variability, like in the ice, that you can detect changes even with relatively short satellite records. So we only start in about the early 1990s with the direct satellite observations. Okay, so here's a picture of scale. Here's Antarctica, here's the 48 states. Okay, so it gives you an idea of how big this place is. It's the United States and Mexico combined, roughly. And in the longer term, so we started here, the longer term here is starting with the International Geophysical Year, 1958, roughly. There's only about 15 sites which have long-term records. Okay? So the question is, what happens here? And I don't know how many weather stations are there in the lower 48, literally thousands, probably. So this is a very data sparse area. Extreme data sparse area. Okay. However, it does turn out that there was this station at Byrd. Okay. Once again, it's the same Byrd we're talking about in the Byrd Polar Research and Climate. Is that right? Byrd Polar. It's their new name. Byrd Polar and Climate Research Centre. We've got to practice that. This is from Admiral Richard E. Byrd, who is the centre's name. And this is the only long-term record from West Antarctica. Okay, and it started off as a manned station in the International Geophysical Year, and some people in the audience actually were there and part of its history. And it was a meteorological station, amongst other things, and the records really were quite very good at that time. Ran for about between 10 and 15 years. Then we had a gap in the 1970s, and then we started up with these satellite transmitting weather stations, which work well when the temperatures are nice and warm, but they're very, very low power. And when the temperature drops and it gets down to something of the order of minus 50 Celsius at this place, it don't work so well. So there is a long-term record here. However, there are a number of gaps. And we worked on this problem that there are not so many as to preclude a reconstruction or interpolation of missing parts. And so one of the papers that we had was to reproduce this. And this is this is very characteristic of weather. This is the reconstructed annual temperature records. It's more complete in some places, it's less complete in others. Okay, but we did some very, very careful work to fill this in. And this is what we get. Okay, it jumps around a lot. See, there's a lot of peaks here, a lot of valleys, and it's this general upward trend that's been going on. If you like drawing straight lines, people love drawing straight lines, then you get an increase, a linear increase at that time period of about 2 degrees. So it's about 4 degrees Fahrenheit between 1958 and 2010. There's a lot more structure than just a straight line there. That red part is just, I think, a 5-year running mean. It's a good running mean. Now, how big a number is that? Doesn't sound like very much. Well, actually, 4 degrees Fahrenheit over this kind of time period is actually quite significant. And so what Julien and myself and Aaron did was to take the records from this data set that's run out of the UK and actually figure out the linear change in these various weather stations around the world. And this is really quite big, actually. It's find similar changes in the northern hemisphere, in the Arctic actually, and not so much in the lower latitudes. Okay, so this is quite a major change over that time period. Very recently, things have been warming up quite dramatically in the Arctic. Okay, but over that time period, that is a substantial change in the annual mean. Okay, so we've got one point, we've got reasonable confidence, we know what's happened at one point. Actually, how do we put this in the big picture? So we're really talking about, as we have those 15 stations, can we take the records from those 15 stations? How big is their footprint? The idea of a footprint, how spatially representative it is. And can we fill in places where we don't have observations? And so people have done various methods of spatial interpolation to deal with this. It does turn out that temperature has a relatively big impact, so you measure something, let's say there, and you're finding out information over a very wide area. There was this quite famous paper now by Eric Steig and colleagues that appeared in Nature in 2009, and they were the first to draw attention basically by doing this extrapolation of this warming of West Antarctica. Previously, and we'd heard this from David Elliott, we knew that there was dramatic change going on in the Antarctic Peninsula, both in the temperature regime and in the ice. And this was the first indication that it was much more widespread than people had thought about previously. Okay, so the general idea of warming in West Antarctica, most people get that. Where it is, how big it is, what season it happens in is rather, that's where the differences come. Okay, so we recently published another analysis of this, and so this was just come out in the Journal of Climate, and so this is a reconstruction of the linear change in temperature from 1958 to 2012. All right, so this is what the picture looks like on the annual mean. This is the southern summer, December, January, February, March, April, May. Southern winter, JJA, and springtime. Okay? And so this tells us, okay, so here's the warming going on in the peninsula area, okay? And once again, it does quite a good job because it's established from the weather records, like at Faraday, for example. And this feature over here is tied to our record from West Antarctica. Okay? If you look on the seasons, what's happening, we know that these are two different phenomena, actually. What's here and what's here. And the reason we can say that the warming along the peninsula happens in the fall, March, April, May. And in the winter, not so much in the spring. In West Antarctica, it happens in the winter and the spring. Somewhat different seasonality. Okay? And you can see spatially, as far as the characteristics go, being different as well. Okay, so looking at West Antarctica versus Greenland. Greenland is this other ice sheet of a similar size. It sits in the North Atlantic, as you well know. Greenland has widespread summer melting every summer now. You can go up and you can see streams that run into the ocean. There'll be ponds that'll sit there through meltwater and then they'll suddenly discharge, or they go into spaces called moulins that go to the bottom of the ice sheet. Is this what the future is going to look like in West Antarctica? Would be. Right now, there's no evidence of increased melting since 1979 in West Antarctica. This is the start of the satellite record that we know from the passive microwave. In the interior of Antarctica, of West Antarctica, it's at 1,500 meters above sea level. It's still very cold in the middle of summer. Only on the rare occasion do you get some melting up there. What matters most is not melting in the interior of West Antarctica, but what's happening down at sea level on those ice shelves, which are close to sea level, doing this holding back of the ice sheet. It turns out that West Antarctica, so this is the causality issue, is that, okay, so here's West Antarctica in the bigger picture of the southern hemisphere with the southern continents, and we have the Pacific Ocean, so it faces the Pacific Ocean. And so there's a lot of things going on here. It turns out to be a very complicated place in the climate system. One of the things that happens here is that you're probably familiar with these El Nino, La Nina events where we get this warming of the sea surface temperatures along the equator, and they affect the thunderstorms, and then the effects propagate into the atmosphere. And then we find these kind of circulation patterns, and all you need to know is it's red there, and then that means the pressure is higher. It's one of these highs and lows, and the flow in the southern hemisphere is counterclockwise. So this is, when you get a pattern like this, it pumps warm air from the ocean into the ice sheet. It's one of the possible causes. Okay, glaciers. This is incontrovertible evidence, or at least according to the glaciologists talk to. Okay, the ice sheet is losing mass. So this is from the GRACE satellite, which is a gravity satellite, which measures the total mass of ice. And it's not much happening anywhere else, but there's a lot of mass loss going on here. Okay? So that's very certain. It only starts in 2002. Okay? But there's indirect evidence that's been going on longer than that. Okay. The glaciers are speeding up. So people can actually track the motion, and I'm not exactly sure how they do this. Interferometry, if anybody knows, probably somebody knows. That you can do, I believe it's like feature tracking or something similar to that. And you can track the motion of these glaciers, and this is Pine Island, and Thwaites is in here, right? These are these two important glaciers in this critical area of West Antarctica. What Terry Hughes called the soft underbelly of West Antarctica. And the reds mean that over this time period of the study, from about 12 years, the speed of the glacier motion has increased in these ice streams. Okay? Also incontrovertible. The ice shelves themselves are thinning. So this is laser altimetry from ISAT, I think, and this measures the height of the glacier surface above sea level. It just measures the range from the satellite to the surface, and the reds mean it's going down or thinning. Okay, so mass is being lost here. The glaciers is speeding up. The ice shelves, which are holding back the ice sheet, thinning. Okay. And grounding lines are retreating. Grounding line is where the ice actually comes in contact with bedrock. And so when you put it all together, there's some quite warm, in Antarctica, warm is +1, +2, +3 maybe degrees C. But for ice, anything above 0 is hot, right? And so we've got this thing called circumpolar deep water sitting just offshore, and it seems that it's getting up under these glaciers that we talked about, the Pine Island and Thwaites glaciers, encouraging them to retreat, and as they retreat, they flow faster and they thin. So it's thought to be this warm, relatively warm water, which sits quite close, not far offshore, it's getting under the ice shelves and causing them to retreat. Now the important point is, you see there's this one point here, right? Where the ice is sitting on that point. And if it gets beyond there, bedrock goes way down. Okay? So in other words, the anchor point for these particular glaciers. And once it retreats beyond there, it goes into this marine ice sheet instability. At least we think it does. Okay? Down, that's what bedrock is sloping into the center of the ocean. Okay, what's causing it to happen? Well, that's a good question. We're almost certain that the atmosphere is playing an important role here. Here's a picture of the westerly winds over the Southern Ocean. This comes from marine analysis, if you're familiar with that. Here's Patagonia right here. So Patagonia ice field is right there. And the westerly winds go around. This is from the southern summer. And they've been changing. And that's what the red shows, that the winds are speeding up here and they're slowing down here. That's what the blues and the reds mean. Okay? So they're speeding up here, slowing down here. What's happening is these are slowly migrating forward. Okay? And this is in the summer once again. And the winds along this are blowing towards the west. Okay? It's an important thing. So the winds, changing winds are blowing from west to east, roughly, along that coast. Okay. So in a counterintuitive way, if the winds are blowing this way, the ocean reacts because of the influence of the Earth's rotation by transporting water to the left and offshore. It's called the Eckland effect. Doesn't matter. But it moves at right angles to the wind force. Okay, so if the winds are blowing from west to east along this coast, it forces the ocean to have flow offshore, and if it flows offshore, it's got to come up from the bottom, which means it's bringing the warm circumpolar deep water onshore under the ice. So, we had some quite dramatic results of, and this is not my work, okay, but there were two papers published in May 2004 by Eric Grignot in Geophysical Research Letters and Ian Jarkin in Science, and they were both, one was a modeling, one was an observational study. If you read the blogs or the media, there were quotes like this. And if you look at the actual papers, then the important point is that present observations of the underlying bedrock combined with model simulation shows there is no stabilizing mechanism that could stop the ongoing retreat of Pine Island and Lakes glaciers, these critical glaciers in West Antarctica. And it looks like, to quote from these people, that the West Antarctic ice sheet has entered the early stages of collapse, right? This marine ice sheet instability hypothesis. And this is slow motion. You go there tomorrow, you probably won't notice any difference, but on the time scale of, well, maybe 200 years, we don't really know, actually, that, but at least there's direct evidence now that this thing is going away. So looking at the longer term, all right, so just looking at the temperatures now, this is the climate. Some people have drilled ice core records here in two places. This is the Waste Divide record. This is another one from down here. This is a proxy of air temperature. We're going to look and see how much really that measures air temperature. But you can see that you would say, oh, well, this is part of some sort of longer term. This is about a 300-year record. There, it does show the warming that was talked about from the Byrd station, but there's a lot of oscillations going. Here we're probably at the upper end of this. This is the Waste Divide, which is close to Byrd station itself. There's lots of ups and downs. Okay, so maybe it's cyclical. Maybe we're close to exiting the upper range of natural variability. Okay, so future sea level rise. Basically, I don't think we have a good idea what this is going to be. This is the model projections from the Intergovernmental Panel on Climate Change. That's mostly from thermal expansion of the water. So you heat up water, it expands, ocean levels come up, and maybe, you know, there's a lot of uncertainty. We don't know what the greenhouse gases are going to do. The models have quite a range of uncertainty, but maybe you get something of the order of 80 centimeters or so. There was this paper that just appeared in environmental research letters where they actually polled people that do this kind of work. So this is some kind of estimate of what it could be based on waking up slumbering ice sheets. And it might be quite a lot bigger by 2100. Okay? So how the ice sheets are going to really respond is quite uncertain in my view. Here's an interesting political thing. So somebody wrote about gravity. Now if you take ice away from West Antarctica, actually sea level drops because there's not as much attraction of the ocean water, but it rises elsewhere. So that's what these, and you should focus on the colors, don't worry about the contours so much, but focus on, so depending on how much, so these reds are around, if you take something like 3 meters, 3.5 meters from West Antarctica, this is how it gets redistributed. Guess what? It doesn't get redistributed equally, and one of the focal points for sea level rise happens to be the Chesapeake Bay. So you don't have to go very far up the Chesapeake Bay to find Washington, D.C. So if this was to come about, there would be some political response, probably. Okay, so I don't know how I'm going on time here. I guess I'm going all right. Okay, so multiple lines of evidence that the climate of West Antarctica has changed in recent decades. This is seen directly from the temperature records and indirectly through changes in the ice and the overall ice sheet mass balance. Trying to find out the cause, there's a lot of arguments as to whether it's regional effects or remote, natural changes versus human-induced changes, or maybe some combination of the two. So far, the direct impact of the increased greenhouse gases in this part of the world has been secondary to changes in the atmosphere circulation. So the atmosphere brings in warm air, temperature goes up. Not that far from the ocean. And right now, the ocean is the primary direct driver of West Antarctic ice loss, that is ultimately driven by the winds. Okay. So what could we see in the future? Well, that's a good question, isn't it? It's possible that the atmosphere could warm up to the point where surface melting over the ice shelves starts to accelerate. And we've already seen from the ice shelves in the peninsula what dramatic changes that can happen. Basically, these things disintegrate, they shatter into millions of pieces. So if this was to happen on, the ice shelves around West Antarctica, you would almost certainly get a major response of the ocean. What would be the timescale of, we've talked about collapse, a threat. What is the real timescale? Now, as I've listened to talks by glaciologists, the timescale has got shorter. They used to think that it was very, very long. Nothing happened on us. And I think the wake-up call came when the Larsen B ice shelf collapsed in front of everybody's eyes. So how quickly could this occur? To be provocative, I put decades, and then I put a question mark after that. It could be as long as thousands of years. or it could be something in between. Nobody has ever seen one of these marine ice sheets go. We know that they've gone, but how quickly, we don't have a good idea. And if you lower an ice sheet, right, you start to increase the temperatures. So once you start doing that, then you get a lot of the surface processes like meltwater runoff could kick in. So just as a final thought here, that, okay, this is a famous physics experiment. It's called unstable equilibrium. And you might want to think about the West Antarctic ice sheet sitting on top of this mountain. And we know it's unstable from the records of the Union and longer ago. And you may only take a little bit of a nudge to kind of push it off the unstable equilibrium. So whether that's natural variability, it would go away anyway, maybe, or maybe the human-induced influences will amplify this. That's probably very likely. And so how quickly is it going to go down the hill is the basic question. Okay, so the anthropogenic nudge is clearly there. Okay, so that's all I have to say. And I guess we're right about on time and we can have some discussions.